Hey guys, welcome back to our series on cracking the coding interview. Today we're going to be solving a problem called remove duplicates, but keep a few things in mind. First is, this problem also happens to be a LeetCode problem. Feel free to pause this just to read through and make sure. The only difference is LeetCode asks us to do it for a sorted list. However, this problem asks us to do it for an unsorted list. However, the algorithm we're going to develop is going to work regardless of if the list is sorted or unsorted, and by list I mean linked list. Also, keep in mind we solved this problem before using a buffer, meaning we ignored this follow-up saying we're not allowed to use a buffer, and we also ignored this saying to use 2 pointers, meaning we only followed this saying, hey, use a hash table. Today we're going to use an actual hash table. In our previous solution we used a set, and we'll see what the difference is. Without further ado, let me go ahead and explain how we intend to solve this problem. Some people, including LeetCode, assume the head of the list to be right here. However, I don't like that. I like to assume there's always a node in front that contains a value called none, and that is, well, not a value called none, contains the value of none, and that is the head. So we're going to implement it this way for our solution. However, for LeetCode, we're going to implement it LeetCode's way, that this is the head of the list. So here's how we're going to do it. First, I'm going to define an empty hash table called items, and I'm going to set him equal to an empty hash table first. But as soon as I define him, I'm going to initialize him with this. We're going to use a variable called current. As soon as I create my hash table, I'm going to put in the value of current and map into the value of 1. So every element in my hash map is going to be mapped to the value of 1. Okay, then we're going to start iterating through this. Current at index, okay, he's at index 0, okay, so which is right here where current is. Current is index 0. Keep in mind, linked lists really don't use the concept of indices, but it just helps this explanation be a little bit smoother. And also ignore the fact that I'm using a sorted list for the example. Again, this algorithm is going to work regardless of if the list is sorted or not sorted. I just think sorted lists look slightly cleaner. When current is at index 0, we're going to ask ourselves the question. At every iteration, we're going to ask this question. Is current.next.value? Is the next value of current in our dictionary? Is he in items? In this case, the next value is this guy. Is current.next in dictionary? So yes, obviously 1 is here. So the answer is yes. In the case of yes, what do? We're just simply going to say current.next equals current.next. So what this line effectively does is, every time you see a next on the left side of the equal sign, it breaks the pointer and points to something else. So what this does is it breaks this pointer right here on current.next and points it to current.next.next. So this is pretty much what the linked list is going to look like after executing that line of code. So now current.next points to current.next.next points right here. So effectively that deletes this guy technically from our list, although he's still in memory, but he's deleted from the list because nobody's next pointer is pointed to him. Then we're going to go on to the next iteration. In our next iteration, current is still at index 0. Okay, current hasn't moved yet. His next pointer just moved. We're going to ask ourselves the same question we asked in the previous iteration. Is current.next.value in our dictionary? In this case, current.next, we broke the pointer, so .next is now this guy. Is this value is 2 in our dictionary? The answer is no. What do we do when the answer is no? The first thing we do when the answer is no is to add him. I'm just going to say val here, but just whenever you see this val, just know he represents current.next.value. So we're going to add him to a dictionary and set him to a value of 1. So pretty much what we're going to do, 2 map 1. Again, it doesn't have to be 1. We keep setting this value. It can be anything. It can be infinity, it can be 10, it can be 12. It's just something to know that, hey, we're adding these values into our dictionary. So after this, then we're going to move our pointer. We're going to say current is now equal to current.next. So this effectively moves current from right here. Current moves from current to current.next. So now current is right here. So now we're going to go to the next iteration. So now current is at index 2. Current is at index 2. We're going to ask ourselves the exact same question. Is current.next.value in our dictionary? So this is current now. This is current.next. His value is 3. Is 3 in our dictionary? The answer is no. What do we do when it's no? The same thing we did in the previous solution, in the previous iteration where it's no. First thing we do is add him. Items of val is going to be equal to 1. Okay. So keep in mind val just means current.next.val, just don't write it all. So we're going to add 3, map him to 1. Again, it doesn't matter what you map him to, you can map him to wherever you want. It's just easier to do to 1. So now we've mapped it to 1. What do we do next? Same thing we did. We're going to say current is going to be equal to current.next. So this is looking good so far. So current equals current.next. So what that does effectively is move current from right where he is to his next guy. Now we're on to the next iteration, which also happens to be the final iteration. So now I'm going to say current is at index 3. Okay, so what do? We ask the same question we've always asked. Is current.next value in items? Does he exist in our dictionary? In this case, current.next.value is 3. Is 3 in our dictionary? Yes, 3 is already in there. In the case of yes, what do we do? Same thing we did in the previous case of yes. We just said current.next equals current.next.next. Anytime you see a .next on the left side of the equal sign, it just means we're moving the pointer. So we're gonna move the pointer of current.next to current.next.next. So effectively that breaks this pointer and moves him to current.next.next, which happens to be none. At this stage we close our hash map, so this effectively deletes this guy. So we have only returned 1, 2, and 3. Without further ado, let's put this solution to code. I've gone ahead to create our node class, which is the building block of our linked list. Created our linked list, created the append function, which is how we're gonna build the linked list. Obviously, we're just appending different values to it, and created the display function, which is how we're gonna visualize our linked list. So this is the function remove duplicates we're gonna edit to work. So right now we've created the linked list of just random numbers. We're gonna call our function right here. We're displaying the linked list before we call him and after we call him, so that we'll see how he's changed. Right now he hasn't changed, right? If we run this, there's no change because we've done nothing to the linked list. Actually, it's giving us an error because we have this function, let's say pass. So if we run it right now, it's not going to do anything, right? It's going to return the same because we haven't done anything. So I'm going to go ahead and call him right now, even though we haven't done anything. My list remove duplicate. Still not going to do anything because we just passed him. But let's go ahead and edit him, kind of like we just explained on the whiteboard, which is why I like the whiteboard coding, because it's in a lot of software interviews they kind of make you code on the whiteboard. Let's go. So first we're going to initialize our dictionary. We call it items. Okay, we're going to set him to an empty dictionary first. Okay, then we're going to define our current. He's going to be equal to self.head.next. The reason why we start him from head.next is because, again, I like to assume our head is a non-node. Most people, including LeetCode, assume the head is this. So we're not going to say current equals head.next. We're just going to say current equals head. So let's go next. So next, like I said, we're going to populate our items dictionary with the first guy. So items with a key of current.value. So the first guy we're on, which is head.next, which was 1, or in the case of this example, it's going to be 0. We're going to set him to a value of 1. Okay, creating a hash map, our key value pair. So now this is where the actual algorithm begins. So while cur and cur.next, so cur.next is driving our loop. Both of them are. We want to ask the question, is cur.next.value, does he happen to be in our dictionary? Okay, is he in items? If it's a yes, we're just going to say current.next equals current.next.next. It's exactly like we did in the paper for all the yes cases. Current.next equals current.next.next. And then if it's a no, we're going to add him and then set current equals to current.next. Okay, else, which is the case where it's a no, he doesn't exist in there, we're just going to say items of current.next.value equals 1 key value pair, and then we're going to say current equals current.next. Simple. And that's it for our algorithm. Let's go ahead and run this and see what happens. Oh, there's an error. What is the error? The error says node has no attribute value. Oh, okay. This should be current.val. Let's try one more time. Okay, boom. You see how it removes all the duplicates? So it works fine. Let's go ahead and also test it on LeetCode. So this is the exact same code. Only difference is, like I said, current.head is what we mentioned here, rather than in my code where I say self.head.next, right? We don't need that because LeetCode doesn't assume the first node is none like I do. And the second difference is we added a check for if the head node is none. In my case in here, we didn't have to add that because, again, I always assume the first node is none. LeetCode doesn't do that. So in the case where you're given a linked list of only one node, none, we need to add this check. But for my code, that already takes care of it. So let's go ahead and submit this and see how we do. Bam, this code was good in terms of space. We're using so small memory, but in terms of time it wasn't as good, but however it was successful. So that's it for this video. I hope it was helpful, and I'll see you in the next one.